Hello friends, today we'll discuss about computational complexity, which is very helpful in the comparison of two or more algorithms performance. So let us start in the detail. The term computational complexity is made up of two words, that is computation and complexity. The computation involves the problems to be solved and the algorithms to solve them, whereas complexity involves the measure of the performance of an algorithm. That means computational will cover the problem and the complexity will cover the performance of that solution. So the performance of an algorithm depends on many internal and external factors. Internal factors specify algorithm's efficiency in terms of time required to run and space required to run. That means how much time is needed to run the execution, to run the program, and how much space is needed. According to that, we can say the efficiency of which program is better. In the same way, external factors affect the algorithm's performance. These include size of the input, speed of the computer, and quality of the compiler. It means when we give bigger input, so how is the performance of algorithm? That is also one important external factor, size of the input. Speed of the computer, that is also very important. On which computer we are running the program, how is the speed? It is very slow or it is good. So according to that also the performance can vary, and quality of the compiler also. Now estimating complexity of algorithms. Big O notation is used to describe an algorithm's growth rate. The growth rate determines the algorithm's performance when its input size grows. The big O notation is very useful for comparing the performance of two or more algorithms. For example, if we have two algorithms for solving a problem, one has complexity order of n square and the other has complexity order of 2 to the power n, we can now compare the number of steps needed to solve the problem for different sizes as described in following table. So we can see in this table, if one complexity is of n square and another is of 2 to the power n, when the size is 2, both are taking the same number of steps, 4 and 4. But as the size is increased, here size is 5, the n square will take 25 steps, whereas 2 to the power n will take 32 steps. So in this way we can see this is slightly slower and this is faster. Now let us see another size, 10 size, this will take 100 steps, 1024. Now you can see there is a change, huge differences there between the number of steps, and when the size is 50, this will take 2500 steps and this is very big. So now we can say which complexity is better, the order of n square is better. So from the above table, we can say that the algorithm with complexity order of n square is better than the algorithm with complexity order of 2 to the power n for solving the same problem. So like this way we compare two or more algorithms. Now dominant term. Big O notation is used to describe an algorithm's growth rate. The term which is going to affect the most on the algorithm's performance is known as the dominant term. For example, if an algorithm has performance n cube plus n square plus t, where t is a time constant, then we can say that the maximum impact on the algorithm's performance will be of the term n cube. So we can ignore the rest of the terms and simply say that the algorithm has complexity order of n cube. Why the maximum impact on the n cube? As you can see, t is a time constant, so n cube will be always bigger than n square. So that's why here the dominant term is order of n cube. Some common growth rates are there that we can learn also, because some questions are based on the common growth rates, like order of n, linear complexity, linear search example, order of log n, log, binary search. For example, as you know, in binary search, the array is divided into two halves every time. So if the size is 20, it will take maximum 3 steps. That is equivalent to math.log20. This is natural logarithm. So math.log20 is 3. As you can see 20, when in binary search if the size is 20, firstly it will be divided into 10, then 5 and then 2. So 3 comparison maximum. So that's why the binary search complexity is the order of log n. If size is 40, 3.69 mat.log 40 3.69 and rounded it is 4. So if the size is 40, so maximum it can take 4 steps. Order of n square quadratic selection and bubble sort, the complexity is order of n square because nested loop is used. Order of n cube cubic simultaneous linear equations, and order of 2 to power n, which is exponential, the towers of Hanoi problem. The exponential means where the number of steps increases very fast, as you have seen in the previous example. Now calculating complexity. How to calculate? Let us take some examples. Suppose if there is a loop which is running n time and there is a print statement. So how to calculate the complexity of this loop? Let us assume the body of the loop is taking t time to execute it, and because it is running n time, so total time will be t into n. So because t is a time constant, so what will be the order of complexity? Order of n. Another example. Suppose there are two loops, nested loops, both are running n time. So now here let us see if the body of the loop is taking t time. So you can see that it is inside two loops, so the total time will be t into n into n, as it is a nested. So t into n where t is a time constant, so order of n square. Another example, if first loop is running n time and after closing the first loop we have another nested loop that is running n time inner loop and n time outer loop. So how to calculate this? Suppose if the body of the first loop is taking t1 time to execute and the body of the second loop is taking t2 time to execute, so the total time will be n into t1 plus t2 into n into n, because this is running n time, so n into t1 or t1 into n, and this is n into t2. Because t1 and t2 is the time constants, we can ignore it, and then order of n plus n square. Now you can see here dominant term n and n square. Definitely n square will have more impact on the algorithm's performance, so that's why a dominant term is n square. So the order of complexity is order of n square. Worst case complexity. The worst case complexity of the algorithm is the function defined by the maximum number of steps taken on any instance. It provides an upper bound on running time. Means what is the maximum number of steps that is taken by the algorithm, that is known as worst case. Best case complexity. The best case complexity of the algorithm is the function defined by the minimum number of steps taken on an instance. It provides the time of optimal performance. Means for best performance, what is the minimum number of times required by the algorithm, that is known as best case complexity. Average case complexity. The average case complexity of the algorithm is the function defined by the average number of steps taken on any instance. It provides expected running time. So basically, according to the average case complexity, we decide which algorithms is going to give better performance. So let us see with the help of example. If we take the example of linear search and binary search, if the size of array is 20, as you can see the worst case complexity will be 20. Why? Because maximum 20 comparison may be required. And if the size is 40, so worst case complexity will be 40 because maximum 40 comparison is possible, because maybe the number is present at the last index. But in binary search, you see, if the size is 20, as we have discussed, mat.log 20 is 3, so it can take 3 steps, whereas size is 40, it can take 4 steps. Why? Because when size 40 is divided into two halves, then it will become size 30. So you can see there is a very slight change. When size is double in linear search, in worst case complexity, the number of steps is also doubled, but in binary search, it is just one step is increased. And best case, so obviously it will be one only, maybe key the element which we are searching is found at the very first element in either in linear or binary search. So best case complexity will be one comparison, but worst case according to the size it is different. So this we can see with the help of graph also. Like in In best case, as the input size grows, the number of steps slightly changes, and in worst case, if the input size grows, the number of steps, a drastic changes in the number of steps. So this is all about complexity. I hope you like the video. Thank you.